Alright, in this additional supplemental exercise, I've been asked to help you go through some of the nuances of the free body diagrams and the answers. So let's take a closer look at this. Notice we've got the ski lift type of situation, the cable car that's pulling passengers along. This is the carrier cable, ED. This is the towing cable, AC. And so in this kind of scenario, being a cable, we're tugging on that, and then we're tugging on this cable, but it's the same cable and it's not tied off there, so the force in that cable is same magnitude but different orientation. And of course we have then some sort of mass that then creates a gravitational force. That's W equals mg. Well, let's go figure out what that is. We got 400 kilograms times 9.81 meters per second squared for acceleration of gravity. Even up in the air, although it might change just slightly, it's not going to be significantly different. And we're going to get that that's 3,924 newtons, or 3.92 kilonewtons for the weight. All right, so that's the driver. So if we're going to guess the force in the force in cable ED, I'd look at that and I'd say I've got to split the effect of this weight into two kind of components, 10 degrees versus 20 degrees. The x components of that, or not the x components have to balance on these two, or do they? Wow, confusing, huh? Well, they're pretty close to being in line. What if I just ignore that and say, I'm going to say that the y component of this force goes entirely into AC, and so I'm going to guess that TAC is approximately going to be equal to the W divided by, well, I want the opposite, so that's sine of 20 degrees. Now that's not the cable we wanted, but so I don't know how helpful this really turns out to be. But it gets me thinking about scale. Now we're up to about 11.5 kilonewtons in TAC. Well, now I go back and say, the difference in the two x components of these two, of the T, have to balance this big old x component that we've got here, which is going to be 11.5 times cosine of 20. And, wow. So that's about 10.7-ish, 10.8, about 11. All in here in this T, that gets kind of confusing here. So, the one that we're dealing with is T cosine of 20 degrees minus T cosine of 10 degrees. Its absolute value is got to be 11.5. And, wow, 11.5 divided by 20 cosine minus 10 cosine. And I've got that minus sign in there. But wow, we go up to T being an ED being about 255 kilonewtons. Wow, it's pretty large, starting here from 3.9. But this is a pretty flat cable that's carrying a whole heck of a lot of load. So, interesting. Let's dig into this a lot more carefully now. Okay, so we're going to have to deal with two different free body diagrams, and we'll go to the pulley at B. We have let's draw a horizontal reference line here. We've got the tension in the pulley, or not the pulley, but the cable coming off here at 10 degrees, and we've got one coming on the other side at 20 degrees. Oops, that's T, that's 20 degrees. And we've got some sort of force tugging, pulling right here. Right, now we'll call that force in AB. And notice something important here, and that is that those three have to form a little triangle, equilibrium triangle, where two of the sides are going to be the same value. It's an isosceles triangle. And so we're going to have this force here, and one that's coming down. This T will be coming at 10 degrees from the horizontal, and this one goes up. That's T, and this one down here is at 20 degrees from the horizontal. The top one is at 10 degrees, so that means this interior angle has to be 10 degrees. And so that's kind of interesting. And being an isosceles triangle, then the sum of those two is 170. Half of 170 is what, 85? Oops. Yeah, that's right. 170 divided by 2, 85. So that force FBA, then I now know its orientation. It's an interior angle there at 85 degrees. And so if we work this out, we got 10 degrees right there. Over to this one, swing that over 85 degrees. What's that going to mean? It's going to mean that from the vertical, this angle right in there is going to be 15 degrees. Now how did I get that? Well, if I had turned a right angle here, then I would have had 10 and 10, but I'm 5 degrees less than the right angle, so that makes that have to be from the vertical 15 degrees to get to FBA. Right? If you're not quite convinced of that yet, just plot out all of the little various pieces and you'll get there. In other words, notice it's an average of those two. You've got to split those angles, bisect them when those tensions in the cables are the same. That pulley's just riding along there. Okay, so that's one part of a free body diagram. And we can do some other things here, law of sines, to relate those things, but let's go do the other free body diagram, which is down below. There's your FAB. There's point A, and we've got TAC kicking off at 20 degrees. And of course we have the weight coming down here at 3.92 kilonewtons. Right, so those all have to work together. There's your 20 degrees, there's your 15 degrees, and if I do the force triangle there, what are we going to get? Right, I could do sum of forces in the x and the y and the z and do all that. I'm not sure I want to fuss around with that. Just do some force triangle work. Right, so we've got that one, and then that means we're going to have this one to close off at 20 degrees. So let's see how, okay, we'll do that. And then this comes up at 15 degrees. So there's your 3.92, there's your TAC, and there's your FAB. Right, so the x components of A and B and AC have to be equal and opposite in order to get all the way back around. And now I just need to start figuring out some additional angles here. That's 15 degrees. This is 20 from the horizontal, so that means that one's 70 degrees. 70 plus that, 15 is 185, so that means this one right in there is 95 degrees. So now what I can find out is that FAB over here is equal to its opposite angle, that's over here at 70, sometimes it's hard to find that, divided by the sine of 15 degrees. Whew, that's going to be a small number, and we're dividing by, times the 3.92 times 70 sine, that'll be a big number, divided by 15 sine, little number, kicking that up to a big healthy 14.23. Right? So that would be FAB. Kilonewtons. Right? TAC then is equal to the sine of 15, that's opposite. That's not right, is it? No, it's not. Because that is not the opposite of the 3.92. You probably picked up on that. So I got that wrong. That means this is wrong. 70 sine divided by 95 sine times 3.92, it's quite a bit smaller, 3.70 and 3.70. Right? Then let's do AC. That's where the 15 degrees gets in there. Sine of 95 degrees and then 3.92. That's going to be much smaller. 15 sine divided by 95 sine times 3.92, and we get 1.02 kilonewtons. So not very big. So I'm way off here. Man, I don't know what I was doing, but that was a really, looks like a really poor way to have tried to guesstimate all that, trying to go really fast, and looks like I'm way off. So now that's TAC equals 1.02, and that makes sense. It's small when you look at this force triangle. Now we come up here, and if FBA is 3.7, then we do expect T to get quite a bit bigger given the angles that we've got here. So again, it's isosceles triangle, so T is equal to the sine of its opposite angle, that's sine of 85 degrees, divided by sine of 10 degrees times FBA, which was 3.70, and so 85 sine 85 sine divided by 10 sine times 3.7, and we get 21.2. So nowhere even close to the answers in our guess, because apparently made a really flaky model. That's the way it goes. I'd like to know a little bit better about what was so screwy about it. We took the x component, let's see, we took all the vertical component of AC, the vertical component of AC was the only thing that picked up any force this whole entire weight, and that's just not the way it works, right? You're transferring a lot of force into the big vertical piece here, and that's why this is wrong, is that that's not what's going on at all, right? So the link AB participates significantly in the gravity load support at A. In fact, most of the effect of this weight goes into link AB, right? We've got this 3.92 going downwards, turns into 3.7 going diagonally into AB. So most of it goes over there because, of course, AB is mostly vertical. And the towing line needs to be a small value, not a large value. We did have that ratio kind of right, but there was very poor statics modeling going on here. Yeah, there's a difference in this x component that has to be associated with the vertical load carrying, so I was really on the fly doing something associated with this little triangle, but didn't really think through carefully about what happens down here at A, and that's why the differences are so large, right? But both of them end up contributing. Why can't I turn it on? There, finally got the mouse.